Hi, I'm Casper Mazure, R&D engineer at Vantage, and today I'll take you behind the scenes of development of the Vulture Gen5. Now, a new color doesn't make the kite fly high. Aerodynamics does. For the Vulture Gen5, we didn't just tweak the shape. We redesigned the aerodynamics from the inside out. And one of the things we focused on was decreasing the leading edge diameter. This decreased the drag and increased the lift. And this was one of the things we optimized for, increasing lift over drag ratio, also known as CL over CD. But what does it mean in real life? Well, it gives you more vertical pull, less downwind pull, and it enables also to go more upwind. By decreasing the leading edge diameter, the weight also decreased, so it improved the kite's low end. And the kite became also more responsive, but more on that later in the video. One of the special things about the Vulture Gen5 series is that each kite has its own SB aerodynamic profile. So we didn't use the same profile for each kite size, but we optimized it individually based on the leading edge diameter and the wind range you fly the kite in. The goal? Again, to optimize for lift over drag ratio and to postpone stall. Stall happens when the angle between the kite and the airflow gets too high, and the air can no longer follow the shape of the kite. We want to avoid this, as the lift drops instantly. By choosing profiles which can reach high angles of attack, the Vulture Gen5 recovers much quicker after a loop and is also less sensitive against stall when you sheet in the bar, especially in low wind conditions. This was made possible by simulating over 200,000 simulations of different profiles, different angles of attack, and in different wind conditions. But because a kite isn't a 2D airfoil, but a 3D flying wing, we also analyzed the lift distribution along the span of the kite. Therefore, we use 3D fast aerodynamic simulations to test multiple arc shapes and planforms. You could also compare this to Formula 1. You don't just go to the grid and test 10 random cars, but you simulate over thousands to win a race, and that's the same that we did. If we took a look at the simulations, it gave us the insight and the confirmation that we need to find a balance between the vertical lift and turning speed of the kite. And this helped us then to optimize for vertical lift and fast loops. At the final design step, we perform CFD, or computational fluid dynamics. But because this is a very computational expensive step, we only use it to analyze local phenomena. For example, the pressure over the kite. In blue, you can see the lower pressure, and in red, on the underside, you can see the higher pressure, and this generates lift. You can also see the streamlines on top of the kite, and this indicates the speed of the air flowing around the kite. In the back, you can see the turbulence intensity, and in red, this indicates higher turbulence intensity, and this dissipates to the back, in blue, which indicates lower turbulence intensities. Small details matter, so that's why we implemented patterns at the trailing edge to reduce flutter. Flutter is a fast vibration of the canopy trailing edge. By reducing this, we reduce the drag, but also increase the long-term durability of the trailing edge. For the material, we didn't sacrifice on strength and durability by choosing lighter materials. Instead, we optimized for structure of the kite, making the kites lighter while keeping the durability of the materials high. This made sure the kite lasts longer and will perform consistently over time. For the leading edge, we used a 152 grams dacron to protect the bladder. The bladder consists of a thick PU material to protect it from puncturing. For the canopy, we used a Tigen triple ripstop material with a high tear resistance. This together brings an 8-meter kite to 2.6 kg. For the high tear resistance of the canopy, we'll show you an experiment how strong it is. Ivan will help me with the demonstration for the difference between a normal triple ripstop and a highly tear resistant triple ripstop, to showcase what could possibly happen with a pinhole. Okay? Yeah. So this is the normal triple ripstop. It easily tears. Okay. And then we have the same thickness.
Gen5 triple ripstop.
The highly tear resistant triple rip.
Oh! Hey!
That's quite a difference.
Easy,
yeah,
shake it. Shake it.
Shake it.
Shake it.
So, how did we lose weight then with structural optimization? Well, we performed structural simulations to showcase where the stress levels are the highest and where deformation takes place. This allowed us to reduce material in places where it isn't needed. For example, in the center of the leading edge. There we reduced the leading edge diameter, enabling greater twisting, resulting in more steering response and faster turns. On the other hand, we increased the leading edge diameter of the wingtip, as during takeoff, the wingtips experience the highest load. And what we want to avoid is the wingtips to deform too much or collapse, and what's also called buckling. So buckling always takes place at the seams of the leading edge tube. And one thing to avoid this is by increasing the leading edge diameter. But besides this, we can also smartly locate the seams along the wingtip. And this can be analyzed by simulating many different configurations and then taking out the configuration that is the most resistant against buckling. So here, for example, you can see a few of those iterations. If we zoom in on the wingtip, now you can see the seams changing location actually. Like this. There's another iteration. Okay. Then if we take a look at the results, you can see here in red where the stresses are the highest concentrated. And we want this to be evenly distributed along the wingtip, and this will be the most resistant design against buckling. What we can also take a look at is the deformation. And here we can see in red where the wingtip deforms the most, and in blue where it deforms the least. And then this information can be fed into the aerodynamic simulation, and then we can have a better prediction of how much lift the tip generates. Once the kite shape is optimized for maximum performance, those forces still need to reach the rider. And that's where the new 12-point bridal system of the Gen 5 come into play. The bridal configuration has a huge influence on how the kite actually feels on the bar. We tune this bridal system with underwater validation in combination with computer simulations to showcase how the forces are distributed along the bridle, also along different angles of attack. Optimizing a bridle is all about balance. Balancing the steering pressure, bar pressure, stability, response, lift, etc. There is no single perfect answer, it's all about the best trade-off. And to tackle this complex problem, we simulate the bridle in a computer to have a better understanding of how the forces are distributed. And here, for example, you can see the Python codes, and we put in the shape of the kite, the bridle configuration, the lengths of the lines, and the angle of attack the bridle has relative to the kites. Here you can see one configuration, but we can also make an animation of it, which you can see here. And here you can see what happens if you sheet in and sheet out with the bar. It moves the bridle with respect to the kite. So instead of guessing, we let the data tell us what works best. This was a look behind the scenes of development of the Vulture Gen5. I hope this gives you a better understanding of what goes into a modern kite design. If you want to try out the new kites or grab a coffee, always welcome at our headquarters in Scheveningen. Let us know what you want to see next, or if you have any questions. Until next time.